Ionization energy and periodic properties. A periodic property, what's a periodic property? By definition in the book, a periodic property is a characteristic of atoms that varies regularly across the periodic table. What does that basically mean? Well, it means that by knowing the way that these properties trend, in other words, if I move left to right, if I move up and down, how they are related to one another on the periodic table, that there's a relationship between the different characteristics. And we're going to talk about three characteristics today. So these three characteristics, you can understand them as periodic properties, meaning if we plot them on, if we look at different elements on the periodic table, and we know how these characteristics change as we look at the periodic table, you should be able to make statements about how strong or weak the forces are relative to one another. It'll make more sense in just a minute, but that's the idea. That I can determine the relationship between certain properties, between certain atoms, by seeing where they are on the periodic table. Type of thing would be, okay, column 2A electrons, how many valence electrons do they have? 2. You know that. Why? It's a periodic property. It's something on the periodic table that when you look at the periodic table, you can determine it based upon its position. Or in this case, these three properties, based upon how the two different elements are relative to one another. We're on page 145, 146, slightly out of order, like I said, so this idea of a periodic property. The first periodic property we're talking about has to do with ionization. The property is ionization energy, but before we talk about ionization energy, you need to understand what ionization is. And we have all been dealing with this term ion, right? And what is an ion? Anybody? What's an ion? I know you're writing right now feverishly, but what is an ion? When we construct an atom, right, and we're anticipating a certain number of components, certain number of protons. Remember, however many protons, that determines what the element is. So there's a certain number of protons, a certain number of neutrons, a certain number of electrons. If we change the number of protons, we're changing what the element is, right? But we've said we can change another particle, and that being if we change the neutrons, we're making isotopes, right? Remember that? If we change the number of neutrons, we're making isotopes of that element. And if we change the number of electrons, we're making ions. The cation, the anion, we've already talked about that. So to make an ion basically means to add or subtract electrons from the atom. So ionization is that process. Ionization is the process where an atom undergoes ionization to become an ion, either pulling electrons to itself or giving up electrons. Metals want to give up electrons, right? Nonmetals want to gain electrons. And the process of giving up or gaining is ionization. Ionization is the process of making ions. The ionization energy is the amount of energy that's needed to take an electron away from an atom. Actually, the way I prefer to think about ionization energy is from the perspective of the atom that is giving up electrons. How strongly does it hold on to its electrons? Okay? It's put in the terms of how much energy is needed to take it away, but guess what? What's needed to take it away is just a fraction greater than the energy that's trying to hold on to it, right? Let's say we put two people up here. We take Zach and Molly, right? We give something to Molly, and she really wants it, and Zach says, I want it more. He grabs a hold of that thing. How much force does he have to put on it to take it away from Molly? Just a little bit more than she's putting into it to hold on to it, right? If he puts a little more force into it to take it away than she's using to hold on to it, he'll get it. Ionization energy looks from the perspective of the atom that has that electron, and they're holding on to it with a certain amount of strength. With a certain amount of energy, they're holding on to the electron. So, for that electron to lose, or excuse me, for that atom to lose that electron, there's a certain amount of energy that has to be applied to take it away, right? So that's, but when you talk about ionization energy, because we're going to talk about another periodic table in just a moment, which is called electronegativity. Electronegativity is from the perspective of the atom that's trying to take. Ionization energy is from the perspective of the atom that's trying to keep the electron, okay? ionization energy. Now, we've talked about metals and nonmetals, and we've already learned that the tendency for metals is what with relation to their electrons, their valence electrons? Do they tend to want to keep them or tend to want to give them away? What charge do metals want to take? Positive. To do that, they have to give up the electrons. Actually, what they're trying to do is get a octet rule valence shell, right? And it's easier for them to give up a couple electrons than to gain a whole bunch of electrons. So we've already said that metals want to give the electrons away. So question to you is, since the atom wants to give electrons away, how hard are they holding on to them? A large amount or a little amount? Okay, I've got one person interacting with me right now, okay? This is kind of frustrating, okay? Less than 10% of the class is participating, so here we go, one more time. I have an atom that's a metal, and it would prefer to give away than get electrons, so it's holding on to its electrons. Is it holding on to them loosely or firmly? Loosely. Loosely, good, thank you. The metal is holding on to the electrons relatively loosely, because in actuality, it would rather lose than get more. Now think about the nonmetals. Nonmetals have a tendency to want to what? Get or give electrons? Get electrons, right? So between the metals and the nonmetals, which one has more energy to hold on to what it has? The nonmetals, right? Good. So as we think about the periodic table, we would anticipate that this left side of the table, the metal side, would have a relatively low ionization energy because it's not working real hard to hold on to them, which means it doesn't take much to take them away. And on the other side of the periodic table, the nonmetal side, there is a much greater ionization energy, meaning they're holding onto their electrons much more firmly, and so it takes a lot more to take them away. And in fact, this is how the trend goes. It's not only left to right increasing, but it's bottom to top increasing. The higher up you are, the greater the ionization energy. The farther to the right you are, the greater the ionization energy. Okay? This is key for you to be able to see ionization energy. What is the trend? The trend is up and right. The trend is up and right. So if I were to look at a periodic table and plot a couple of these elements and say which one has a greater ionization energy, what would you have to do? Based upon where they're plotted, you would see which one is where. Yeah, keep going. Figure it out. The higher and the righter one, right? The one that is higher and righter, that's such a thing. The higherer and the righter, how's that? Well, it'll be equally wrong in both. But the higher and the righter it is, the more ionization energy, the more energy it takes to take it away, which means the more energy it's applying to hold on to it. So example 4.4 in your book. This is over on page 147. Says that a chemist needs to find an element that readily gives up an electron. What does that mean, readily gives up an electron? Gives it up easily, right. It gives it up easily. So if it's giving up the electron easily, what's its ionization energy? High or low? If it gives it up easily, means it's not working too hard to keep it, right? Which means other people don't have to work real hard to get it, which means my ionization energy is going to be low. So I'm going to be looking for elements which are kind of left and kind of low, right? Because up here they're high, down here they're low. Now, it says a chemist needs to find an element that readily gives up an electron. It has a low ionization energy. Which of the following would suit her needs best? He says calcium. So I look at the periodic table and I plot, well, that's one cesium. Am I out of order? That's frustrating. Okay, miss point. Calcium is right there, right? Calcium, let's see at the second one. Yep, it's a miss point. I saw that this morning, and it may be in how it formats, because it keeps the arrow as a graphic, but sometimes reformats the size of the slide. So these may be off a little bit. We'll deal with that as we go. So calcium, it's actually right here. Astatine is over here. or excuse me, arsenic is over there. And what's the third one? Bromine, yeah. Okay, so those are the three elements that are in play. Remember, this arrow is a little bit offset. It should be right here. So of these three elements, calcium, arsenic, and bromine, which one most readily gives up an electron? Sir? Calcium. Right. Calcium has a lower ionization energy. Why? Because it's lefter. It's on the left side where it's lower, because the right side is higher. You see that? And because this arrow is misplaced, these would all be on the same row, right? Same row across. So if we're looking for the one with the highest ionization energy, we look to the one furthest to the right. If we're looking for the lowest ionization energy, we look to the one farthest to the left. And that'll tell us which one has the lowest ionization energy, which means it's holding on to its electrons with the least amount of energy of the three, and it takes the least amount of energy to take its electrons away, because it's not holding on to them as strongly as bromine is. Bromine's not going to give up squat. It's holding on really, really tight. So it takes a lot for somebody to take an electron away from bromine. Okay. And there's that trend up and to the right for ionization energy. So which one is higher and to the right? Find that one, and that's your answer for increasing ionization energy. Or lower ionization energy is to the left and down. But I'm always going to show you the arrow of increasing. Notice the arrowheads up here? It increases in that direction. That's the point. 4.4b. Which of the following holds onto its electrons the tightest? So what is the question really asking? If it holds onto the electrons the tightest, somebody else. Ma'am. So we're looking for the higher ionization energy, right? It holds onto them the tightest. The ones that they offer us are aluminum. Let's see, ALIN, yep, and B. Well, those are our three choices. Which of the following holds onto its electrons the tightest? Now remember, what's the trending here? Up and to the right. Which one is the most up and to the right of those three choices?
B.
Yeah, B. We're looking over at boron, right? B. It's the highestest and the rightestest. Okay? And so it has the highest energy, ionization energy, because of where it is on the periodic table. You see that? It's a periodic property because looking at the periodic table, there's a pattern of characteristics. This pattern, ionization energy, says when you place them on the periodic table, the more high and to the right it is, the higher its ionization energy. Do you see now why helium makes sense to be over here and not over here? Well, as a matter of fact, the next question asks, which element has the highest ionization energy? Of all of them. With that trend, up and to the right, what's the uppest and rightest element on there? Helium, right? Now, if the periodic table put helium over here simply because it was a nonmetal, or excuse me, it is a nonmetal, right? But if we said, wait a minute, I'm thinking in terms of the S shell. This is the 1s2 position. Helium should be over here. Well, talking about valence orbitals, yeah, it should be. But based upon metal, nonmetal, hydrogen should actually be over there, right? But based upon 1s orbital, it's right there. Now, based upon this periodic property of ionization energy, helium needs to be over there, because if it's not over there, it would be the exception to this rule. You see? So we've got competing exceptions with some things. That's why there are exceptions. So helium has the highest ionization energy of the elements. Well, there's another periodic property that you need to become very familiar with. Now there's our answer, helium. Sorry about that. The next periodic property, 4.6, let's do that, I'm sorry. I am a little bit adrenaline this morning, right? And that should probably be 4.7. Man, this is frustrating. Or should it be 4.8 and I'm behind? We went backwards. That's what happened. It's on your owns. Because that's where we're at. That's what I skipped the exam. I went to the example straight to the next section rather than do the on your owns. These are just going to be more examples. We'll do them right now, like we did the last examples, okay? But they're not right in front of you. The examples, the answers, the explanations are right in front of you. On your own, 4.6 says, order the following atoms in terms of increasing ionization energy. First thing I'm going to do is find them on the periodic table, okay? So we find these 4 elements, and I go through and do that pretty quickly for us. There they are. There are the 4 elements that are in play, right? Now, of those 4 elements, the question is, order them in terms of their increasing ionization energy. The trend, again, for ionization energy is increasing up and to the right. I've been asked to put them in the order of increasing ionization energy. Okay? So I'm going to start with which one, the lowest or the highest ionization energy? The lowest one. Good. Which one would that be? CS. I'm going to start with CS. The next one? IR. The next one? Right? Lead. And the next one? Astatine. We're going to write that like this. See? The ionization energy for CS is less than the ionization energy for IR, which is less than the ionization energy for lead, which is less than the ionization energy for astatine. And that's how we show this. Put them in increasing order of ionization energy. There they are in increasing order, and I make sure that I show that they're increasing by giving this greater than sign, right? Because I'm saying this is greater than this, and this is greater than this, and this is greater than that, the open end of my sign. And so that's how I show those 4 elements in increasing ionization energy. Now on your own, 4.7 says, which atom most readily gives up electrons? Based on the property we're on, ionization energy, what is the question asking in terms of ionization energy? Sir? Okay, so it's the loosest holding, right? Which atom most readily or most easily gives up its electrons? We go through and we plot the ones that we're looking at. There's Ca, Be, out of order, Be, Ba, and Ra. I think this is an earlier copy of my PowerPoints. I think that's what happened to me. So I apologize for that. But these are the 4 elements that we're considering. And it's saying which of those most readily gives up its electrons. Which one has the lowest ionization energy? Ma'am? Ra. Right. It's our lowest ionization energy. Why? Because it's the one that's furthest to the left and furthest down. Now, there will be times when these elements may be on a diagonal. You know, they may not be in a perfect column or a perfect row, and you've got to make a call sometimes. Okay? But just make that call. You know, if it's way farther to the left and one up, you got to, you know, kind of struggle with that. But for the most part, they're going to give you those that are either columns or rows and say choose between these for this kind of property and the other periodic properties. All right? Next periodic property is electronegativity. Now, the way I'd like you to think about electronegativity is this. In the way that ionization energy was from the perspective of the atom holding on to its electrons, electronegativity, like I referred to earlier, is the desire of an atom to take somebody else's electron. Okay? The desire to take away another. No. So think about this. In the same way we asked before, metals and nonmetals. Are metals out there looking to take anybody's electrons away? No, they're looking to give them up, right? So its electronegativity is going to be relatively low. Now, nonmetals, are they looking to give up or to get? Are they looking to hold on to, or are they looking to hold on or to give away? Well, they're looking to hold on to, right? Not only hold on to, they're looking to take away. They're looking to get more. So the trend for electronegativity is the same trend as the ionization energy, up and to the right. It's the same exact trend. But it's from the view of the atom that's trying to get the electrons, not the view from the atom that's trying to hold on to its electrons. But the trend is the same. meaning that metals, and specifically high energy level metals, have a very low electronegativity, meaning these folks are trying to get rid of electrons all day long. They're not going to fight to take away anybody else's. Okay? And to the right and higher up, they're looking to steal electrons from whomever they can get them from. And when they find one, they're going to fight for it. It's kind of the way I want you to think about it, okay? So ionization energy and electronegativity. So on your own, 4.8 asks this question. It says, which element desires electrons the most? And this is in terms of electronegativity. It desires the most. Which one is going to try to take away the strongest, right? That's what it's saying. Which one is going to have, in terms of electronegativity, what? High or low? If it's which one is going to have the highest electronegativity? That's the question. And then it gives us the elements to plot. Calcium, let's see, CaAs, potassium, K, and Se, selenium. Okay? Those are the 4 elements. It says which of these desires electrons the most? In the language of electronegativity, which one has the higher electronegativity? And we know the trend is up and to the right, just like with ionization energy. So which one of these is highestest and rightestest? Hopefully that misspeaking helps you, right? Which one is highest and rightest? Furthest, pardon? Se, right. That's our answer. Se. Se has, of these 4, Se has the highest electronegativity. It also has the highest ionization energy, meaning ionization energy, it's going to use the most force to hold on to what it has. Electronegativity, it's going to use the most force to get somebody else's and take it away from them, right? And 4.9? On your own, 4.9 says, order the following in terms of increasing desire for electrons. Again, that term, desire for electrons, means they want them more. They're going to use more energy to take them away. And so in the language we're learning now, what's another way of saying this in terms of electronegativity? Increasing desire could be said as highest electronegativity. The 4, or the 5 are given to us. And we see as we plot them, or locate them rather, that they are all in a column 7A, right? These column 7A elements. The question is, which one desires electrons the most? Or said another way, which one has the highest electronegativity? And the answer is, in that direction. Oh, it says rather not which one the most, it says, or excuse me, I'm on 9, sorry. Increase in electronegativity. We do the same thing we did before, from up and to the right. So to put them in the order of increasing electronegativity would be looking up and right. In this case, they're all vertical, so we're just looking up. And the order would be ATI, BR, CLF in order of increasing electronegativity. And the signs are always open to the one which is greater. And that shows us our sequence of increasing electronegativity. Oh, by the way, this is also based on the periodic property, which has the same trend, the order of increasing ionization energy. It's the same. Okay? That's the trend. And all we're saying here is, relatively speaking, that iodine wants to keep what it has more than astatine. Bromine wants to keep what it has a little bit more than iodine, and so on. And in the same way, iodine is more likely to steal than astatine, and bromine is more likely to use more force to steal than iodine, and chlorine is going to use more force to steal than bromine, and fluorine is going to use more force to steal than chlorine. It's all relative to one another. We're not talking about actual numbers now or specific numbers. It's just the trend that we're looking at. And lastly, atomic radius. And this is all I'm going to do for atomic radius. Boom. Okay? We'll talk about it for a minute, but I'm not going to put any more slides up for atomic radius. This is the trend. So, without me saying another word, since I've burned through my notes already, what is this arrow telling you? How would you describe the periodic trend for atomic radius? Go ahead.
Down is to the left is.
So the radius increases as we go left and down, right? Let's put it that way. The radius increases left and down. You could also say conversely, then the radius decreases as we go right and up. Now let's think about that for just a minute, because there's something here that's a little bit counterintuitive that's taking place. Counterintuitive, that's your English word for today, right? What does counterintuitive mean? Someone. Well, let's break it down. What does it mean if something is intuitive? If I say that it's intuitive, have you ever heard of intuition? Okay, what does it mean if someone has intuition? They have a sense, they don't really know why, but they have a sense of something to be true or something to be happening. You're just using your intuition. And most people believe that women have a much higher sense of intuition than men do, right? They have a much greater sense of what's taking place, maybe in the background, and not really always knowing why they know things, but they tend to know things that they can't explain. Guys tend to know things because, hey, here's the facts. I observed this. I observed this. I deduced this. They come up with, this is the truth. This is what's real. Women, occasionally, at times, they go, you know what? I know there's more going on here than I can simply see and observe, and there's more going on. And frankly, guys, if you find yourself in a relationship like marriage one day where you're with someone for a long period of time, you should trust their intuition. There's something there, okay? What is it? I personally think it has to do with the brain damage that male children go through in their development. You're aware of that, right? The brain damage. We're getting off chemistry for a minute, but we've got time because I burned through my notes. During fetal development, before we're him or her, we're just it. Still person, but we're an it person, we're not neither gender. In our development, when we are genderized, that for males, at that point of development, that our brains received a wash of chemicals. And in that wash of chemicals, part of the chemical process was to sever some of the connections between the right hemisphere and the left hemispheres of our brains, resulting in the ability, you can jokingly say that guys are all brain damaged, because it's true, we don't have a female brain anymore, we have a male brain. A male brain is a modified female brain. A female brain is what we were all started developing with. But we're male brains now because the connections between the right hemisphere and left hemisphere are broken. What does that mean? That means, generally speaking, this isn't everybody, but generally speaking, males are much more sequential, logical thinkers, right? Because we think with our logic, we think with our arty side, but we don't do both at the same time. Because it's two computers operating and communicating, but not communicating as fully as a woman's brain, where the right and left side are fully integrated. And the art and the emotion and the logic are just a big ball of stuff, okay? Which is why there tends to be, when you think about this, why there tends to be a greater degree of emotionalism for females, right? Because they can't separate themselves from the emotion of the issue and simply look at the logic of the issue. And some people see that as a negative, and some people see that as an incredible positive. I believe it's God's design for us as individuals and as people in community that our differences complement one another, right? They're not one's less than the other. Either way, men aren't less and women aren't less. The point being that we are different, and we're different for a reason. And we're different for a reason for our community, and we're different for reasons of our complementarianism with one another. That we supplement and we augment and we help one another. Which is why Mrs. Baker and I, when we come into a situation, we generally see it very differently, because she is multi-processing. She is looking at all these different components. And to a degree, we can too, guys. We can do that to a degree. And we don't know anything else other than in our own mind. Don't you all think that everyone thinks just like you do? And when other people don't think like you do, it's because they're defective, not you? Okay? We all start like that, but if you stop and think that males and females, generally, not everybody, this isn't specific people, I'm talking generally, our brains work differently. And they work differently for a good reason, for good purposes from God. Okay? So that's what's going on. How do we get into this? Well, I started with intuitive, right? Because women have intuition. It's like, how do they think? Do they know why, or do they just get a sense? The intuitive side of you, this sense goes, here's something, it should be like this. Why does it make sense that atomic radius would increase as I go from top to bottom on the periodic table? Why does that make sense? Why should that just be intuitive? Why would, you know what the radius is, right? Let's make sure we know the word too. Radius is from the center to the edge of a circle. So basically what it's saying, atomic radius is how big is the atom? Does it make sense to you that atoms that are down here on the periodic table are bigger than atoms that are up here? And why would that be the case if it does? Think with me for a minute. What's the difference between an atom that's here and an atom that's here? Yes, sir.
Mass number.
Its mass is bigger. It has more of all the components, right? It has more electrons and more protons and more neutrons. It's got a bigger nucleus. Up here, hydrogen, it's got one electron. Okay, down at the bottom, you know, we're filling up P shells and F shells and all kinds of shells, right? Does it make sense? You got more electrons, you need to be a bigger thing, right? You've got to hold more electrons. So if you need to think of it simply as a Bohr or a planetary model, think of it like that. I've got one electron. How big do I have to be? I'm an itty bitty atom, right? Or am I like cesium? I'm trying to carry around all these electrons, all these protons, all these neutrons. And if I'm looking at a vertical column like all the 1A elements, does it make sense to you that the lower you are, the more energy levels you have? First energy level, second energy level, third energy level, fourth energy level. When we think about the Bohr model, it's the first ring, second ring, third ring, fourth ring. We're a little more sophisticated than that now. We know it's orbitals and it's S's and P's and D's and F's. But the idea being, the more electrons you have to manage, the more space you need to manage them in. So, moving from top to bottom, it makes sense that the atom would be small to big as we move from top to bottom. Small to big. That should make sense. What's counterintuitive? What doesn't seem to make sense until you think about it a little bit harder. I know some of you are already smoking, but here we go. But does it make sense that as I move from left to right, that my radius gets smaller? How's that working? Because as I move from left to right, aren't I increasing the number of electrons? But I'm telling you that as you add electrons moving from left to right, your radius gets smaller. But as you add electrons going from top to bottom, your radius gets bigger. And here's why. Because as you're moving from left to right across in a row, you're not adding energy levels. You're adding electrons. But for every electron you add, you also add a proton, right? And you're increasing the positive charge of the nucleus. And you're not adding any more bands. You're not adding any more distancing. All you're doing is adding more pieces. And so the concentration of the protons in the nucleus can actually pull the electrons in a little bit tighter. Think of it that way. If I'm not increasing the energy levels, I'm just increasing the electrons in the energy levels I already have, or lower ones when we get to the Ds and so on, then my radius actually shrinks. Once I add that one more electron to go out to the next energy level, that's my S shell, boom. Now I'm big again, right? So the trend is from top to bottom is small to big. And the trend from left to right is big to small. My smallest radius, my smaller radius, is going to tend to be up and to the right. And my larger radius is going to be to the left and down. One way to remember this simply, if you can't remember the technical reasons why, and I'm not saying you won't be asked to give the technical reason why, but the quick way to remember this is just remember that ionization energy and electronegativity are up and right. And atomic radius is the other way, down and left. So Ionization energy increases periodically up and right. Electronegativity increases up and right. Atomic radius is the opposite. It increases as we go left and as we go down. Now, I don't have a slide for these, but let's go ahead and look at 410 then. Let me back up so I can get a periodic table up here. I know it says 4.9, but we're actually doing 4.10. Which element is the largest? We're going to do this manually. I'll just point to them on the board. Which is the largest? Calcium. So we've got Ca. What's the second? Astatine. It's over here. As. Between these two, which is the largest? Everybody? Between these two, which is larger?
Calcium.
That was good. I heard 1.5 voices say calcium out of all of you. So calcium is bigger than astatine, right? So I'm trying to find the biggest, right? The largest. So between those two, my winner is calcium. What's the next one? Potassium. Between these two, which one is the largest? Potassium, right? Why? It's lefter. It's bigger because it's lefter, because we're talking radius, which increases left and down. So potassium is my winner between those two. And Se. Where's he at? Right over here. So between these two, which is the bigger? Potassium. So who wins? Potassium. Of those four, potassium has the largest radius. Why? It's the most left. And since these are all in a row, it's the leftmost one. If they were vertical, it'd be the lowest one to be the largest radius. Second question asks, order the following in terms of increasing atomic radius. And they are basically the column 7 elements, aren't they? Br, Cl, I, At, and F, bromine, chlorine, iodine, astatine, and fluoride. They are these 5 elements there. In order of increasing atomic radius, since the trend is left and down, my order of increasing radius would be what? Yeah, just read it top to bottom. Fluorine is less than, chlorine yeah, fluorine is less than, chlorine is less than, bromine is less than, iodine is less than astatine. Okay? The largest radius would be astatine, At. The smallest of those would be fluorine, F, on the top. Why? Because the increasing trend for radius is to the left and down. Are there any questions on those 3 periodic properties? Could you, if given 2 or 3 elements, go to a periodic table and determine which of those elements has the greatest ionization energy or the lower ionization energy, the greater electronegativity or the lower electronegativity, or the higher atomic radius or the lower atomic radius, based upon where they are on the periodic table? Okay, if the answer is yes, then we can move on, and you've covered that material.